Hello everybody and welcome back to another CIV 398 assignment tutorial. So in this assignment tutorial we're going to be covering question 6, which is the bonus question of assignment number 3. So as you guys remember, assignment number 3 hasn't been too bad so far. Question 5 had a little bit of tricks, but other than that it hasn't been too bad. Well, I'm about to change that right now with question 6. I'm sorry, it's a disgusting proof question. I know that you guys really don't like proof questions, but again, it'll really help your understanding of what exactly we're talking about. And this is a fun proof because, as you guys will see later on when we start talking about strains, you're going to think, wait, this makes no sense. So we're going to make sure that you guys know what happens in question 6, and then once we get into later weeks, you're going to wonder if everything is just a lie. It's quite funny what happens, and I'll tell you what happens after we prove it. So question number 6 says, consider the kinematic equation of motion representing rigid body rotation about the origin. So x is equal to q times big X, where q is that nice rotation matrix. And it says, prove that under this motion there is no change in distance between any pair of material points. And of course this makes sense. If I take an object, let's say a nice big giant cube, and I rotate it, well, the 2 points on the cube aren't going to change their distance because I'm not compressing the cube, I'm not stretching the cube, I'm just simply rotating it. And the reason why it says this kind of sounds funny later on is because you'll find out that a rotation matrix, which again just rotates an object, nothing special, it actually creates strain on the object mathematically. So mathematically, our strain matrix will report some strains, but as you guys know, the strain should be 0. So this is where the math and reality start to diverge a little bit. But back to the question. So our goal here is to prove that there's no change in distance between any pair of points on the object. So let's consider 2 points on the body, which I'll call x1 and x2. And we know that x1 is just a coordinate transformation of big X, so that's why we just multiply it by that q. So if we want the vector between these 2 points, it's very simple. Remember in H130 how we did those position vectors? Well, we just take the coordinates of one point of where it ends up, and then we subtract the coordinates of where it started. So let's say I wanted delta x. So this delta x will be a vector between those 2 points. It'll be my final coordinate, which is x2, minus my initial coordinate, which is x1. And as you guys remember, if we have a position vector, well, the magnitude or the norm of that position vector, that is the distance between the 2 points on that position vector. So in this case, if delta x is my position vector between those 2 points, then the distance between these 2 points is simply the magnitude or the norm of that vector. So in essence, if the norm of delta x is the distance between the 2 points, we need to prove that the norm of delta x is equal to the norm of, I guess, bigger X. I guess bigger X is what I call it. So it sounds pretty simple. We're just proving that the norm of these two are equal. But here's the hint for you guys. If we go the norm of x squared, that's equal to x dot x. And we can prove that this is equal to the norm of big X squared. So there's going to be the hint. And what's going to happen is when we go delta x dot delta x, you guys will see that we can use some of the relationships within the dot product to try and make that Q matrix disappear. So there's the hint to you guys. I explained this brutally in the seminar. For those of you in seminar E1, I really apologize for that. Hopefully this can help and make more sense of it. So thank you guys so much for listening. I will see you guys in assignment number 4.